Hello! Welcome to today's lesson on power. Today, we will understand the concept of power as the rate of doing work, or transferring energy, and how it's calculated, and apply the formula for power in different contexts. So far, you are familiar with the concept of work done as a measure of the energy involved in moving something. Building on this foundation, we can now explore the concept of power. Understanding power will deepen our grasp of how efficiently energy is used to perform work, advancing our overall comprehension of physical processes. To start, let's try to grasp the concept of power in an intuitive way. Imagine two cranes, each tasked with lifting an elephant of the same weight to the top of an identical building. Even though both cranes carry out the same amount of work, one completes the task faster than the other. The crane that accomplishes this more quickly is the more powerful crane because it does the same amount of work in a shorter amount of time. So, intuitively, power is all about how fast work is being done or how fast energy is being transferred. The quicker the work is done, the more power is involved. Mathematically, we define power as the rate at which work is done or energy is transferred. The formula for power is power equals work done over time taken. Or we can use the formula power equals energy transferred over time taken. With this, we can see that power increases if more work is done or if the work is done in less time. Let's break down each component of the formula. Work done is the amount of work or energy transferred, measured in joules. Time is the duration over which the work is done or the energy is transferred, measured in seconds. Power is measured in watts. Watts are the units of power, where 1 watt equals an energy transfer of 1 joule per second. To ensure we understand, let's try a simple example. A person pushes a box with a force that does 300 joules of work. It takes them 10 seconds to move the box. What is the person's power in moving the box? First, we start by identifying the key information provided in the problem. The work done on the box is 300 joules, and the time taken to move the box is 10 seconds. Next, we need to clarify what the problem is asking us to find. In this question, we need to find the person's power, which is the rate at which they do work. To solve this problem, we will use the power formula. Power equals work done over time. Finally, we can plug the given values in. Power equals 300 over 10, which gives 30 watts. So the person's power in moving the box is 30 watts. This means they are doing work at a rate of 30 joules per second to move the box. If we were instead given energy transferred, the process would be very similar. Let's look at another example. Suppose we are told that a heater transfers 9,000 joules of heat energy into the surroundings in 30 seconds. What is the power of the heater? First, we start by identifying the key information provided in the problem. The energy transferred by the heater is 9,000 joules, and the time taken to transfer this energy is 30 seconds. To solve this problem, we will use the power formula with energy transferred. Power is equal to energy transferred over time taken. Now, we can plug the values from the question into this formula, so we get power is equal to 9,000 over 30, which equals 300 watts. The power of the heater is therefore 300 watts. This means the heater is transferring energy at a rate of 300 joules per second. Understanding power is essential as it helps us evaluate how quickly tasks can be completed or how fast energy can be utilized. In everyday life, many devices, such as electrical items, come with a power rating. This rating helps us understand its energy consumption, helping us to choose the right device for our needs. For example, if you are choosing between two microwaves, you might notice one has a power rating of 800 watts, meaning it converts 800 joules of electrical energy into heat every second, and another has a rating of 1200 watts, meaning it converts 1200 joules of electrical energy into heat every second. The higher rated microwave will cook food faster, as it can convert electrical energy into heat more quickly. However, it will also consume more electricity, increasing usage and energy costs. Knowing how fast a device uses its energy allows scientists and engineers to assess its performance and make improvements. The concept of power has been instrumental in driving technological advancements throughout history, particularly during the Industrial Revolution. For example, the development of the steam engine by James Watt was a significant milestone in the 18th century. By understanding and applying the concept of power, Watt was able to improve the output of steam engines, making them more powerful and capable of performing more work in less time. This advancement revolutionized industries, enabling factories to produce goods on a much larger scale and at a faster rate. Watt's work on steam engines also led to the introduction of the term horsepower as a unit of power, which allowed people to compare the performance of engines to that of horses, the primary source of power at the time. This concept of power and its practical applications played a crucial role in the widespread adoption of steam engines, leading to significant economic growth and the transformation of societies during the Industrial Revolution. In modern times, this same principle of assessing power and energy usage helps engineers optimize the performance of everything from household appliances to advanced industrial machinery, ensuring that they operate efficiently and effectively. Let's now apply what we've learned to a few specific problems to consolidate our new knowledge. An electric kettle heats water using 300,000 joules of energy, and it takes 600 seconds. We need to find its power. First, identify the quantities provided and their units. The work done is 300,000 joules and the time is 600 seconds. Next, we apply the power formula. Power is equal to work done over time. So subbing in the numbers we get, power is equal to 300,000 joules divided by 600 seconds, which equals 500 watts. So this is a 500 watt kettle. Let's look at another question. A force of 10 newtons moves a box 5 meters in a duration of 2 seconds. We need to find the power. First, identify the quantities provided and their units. The force is 10 newtons, the distance is 5 meters, and the time taken is 2 seconds. In this case, we aren't directly given the work done. Instead, we are given a force and a distance. We can use those two quantities to calculate the work done using the equation. Work done equals force times distance. Subbing in our values gives us work done equals 10 newtons multiplied by 5 meters, which equals 50 joules. Now we can apply the power formula. Power equals work done over time. Therefore, power is equal to 50 joules divided by 2 seconds, giving us 25 watts. By working through these examples, we see how power calculations involve picking relevant quantities and using the correct formula or formulas as needed. Understanding this process helps to solve many practical problems in physics effectively. In today's lesson, we delved into the concept of power. We examined the power formula, which is power equals work done over time, and discussed the significance of each quantity involved. We emphasize the importance of power in various real-world applications, such as engineering and household energy consumption. To solidify our understanding, we covered multiple examples of varying complexity. In summary, today's lesson provided a comprehensive overview of power, thereby enriching our understanding of energy and its use in everyday life.